Have you ever wondered what light really is? An everyday phenomenon yet shrouded in mystery, light is an essential element of our lives, bathing our world in vibrant colors, guiding us through darkness, and even powering our modern technologies. Its importance cannot be overstated. Yet, what do we truly know about light? To answer this, we must journey back in time, charting the course of human understanding. From the earliest philosophers pondering the glow of a simple flame, to the most brilliant minds of today, unraveling the enigma of light in the farthest reaches of the universe. This journey is filled with twists and turns, with theories challenged, discarded, and resurrected. It's a tale of human curiosity and relentless pursuit of knowledge. It's a testament to our desire to unlock the secrets of the universe. From the flicker of a candle to the vast expanse of the cosmos, light continues to captivate and mystify us. The fascination with light dates back to the ancient times. The Greeks, for example, held a fascinating theory that our eyes emit light, enabling us to see. This idea, known as the emission theory, proposed that vision was a result of light beams emanating from the eyes and interacting with the objects in our sight. Meanwhile, in ancient China, the philosophy of yin and yang played a significant role in the understanding of light. They believed light to be a balance between the yin, representing darkness, and the yang, symbolizing brightness. This equilibrium between the two opposing yet complementary forces was thought to be essential for vision. On the other hand, the Egyptians perceived light as a manifestation of the sun god, Ra, illuminating the world and making life possible. These early theories, while intriguing, were just the beginning of our journey to understand light. Each theory, in its own way, contributed to the rich tapestry of our understanding, paving the way for further exploration and discovery. Fast forward to the 17th century, a new theory emerged. This was the wave theory, sparked by the mind of Christian Huygens. He proposed that light was not a stream of particles as previously thought, but rather a series of waves. These waves, he suggested, spread out in all directions, much like ripples in a pond. To Huygens, light was a disturbance in the ether, an invisible, weightless medium that filled all of space. His theory found wide acceptance, particularly when it was used to explain the phenomena of interference and diffraction, phenomena that couldn't be explained by the particle theory. For almost 2 centuries, the wave theory reigned supreme, painting our understanding of light with broad, undulating strokes. It seemed to explain the properties of light elegantly and provided a framework for future research. But as with all scientific theories, it wasn't flawless. The wave theory seemed to explain the properties of light, but not all of them. Enter Isaac Newton with a revolutionary concept. This eminent scientist, known for his laws of motion and gravity, had a different take on light. He proposed the particle or corpuscular theory of light. According to Newton, light was composed of tiny particles, or corpuscles, that traveled in straight lines. This theory elegantly explained reflection and refraction, phenomena we commonly observe in mirrors and prisms. Newton's particle theory, however, wasn't without its critics. Some scientists pointed out that it couldn't account for the interference and diffraction of light, phenomena that seemed more in line with a wave theory. Despite these criticisms, Newton's particle theory had a profound impact on our understanding of light and even paved the way for later developments in quantum mechanics. Newton's theory brought us closer to understanding light, but the mystery remained. A new perspective was needed to reconcile the wave and particle properties of light, leading to a thrilling chapter in the history of light. In the 19th century, the view of light took another turn. A physicist named James Clerk Maxwell began to unravel the mysteries of light even further. He proposed that light was not just a wave, nor was it just particles, but rather it was an electromagnetic wave. This meant that light was a form of energy that moved in a way similar to waves in the ocean, but also carried electrical and magnetic properties. Maxwell's equations, as they are now known, suggested that light was a self-sustaining wave capable of moving through space. Essentially, light could create its own path. This was a groundbreaking revelation that transformed our understanding of light and paved the way for much of modern physics. So through Maxwell's eyes, light became a symphony of electric and magnetic fields oscillating in harmony, propagating through space and time. Light, as it turns out, was more than just waves or particles. As the 20th century dawned, a new theory emerged that would change everything. Enter quantum theory. This groundbreaking idea introduced us to photons, the fundamental particles of light. It was unlike anything we had ever seen. Like an actor playing two roles at once, light demonstrated a dual nature, acting as both a particle and a wave. Imagine a sea of particles, each carrying a specific amount of energy. These particles, these photons, are the building blocks of light. They are discrete individual packets of energy, just like particles. Yet they also exhibit wave-like behavior, spreading out and interfering with each other, creating patterns of light and dark. Quantum theory was a marvel, a revelation that shook the scientific community to its core. It turned our understanding of light on its head, and yet it didn't answer every question. The quantum theory was a leap forward, but it didn't solve all the puzzles. One of the most fascinating aspects of light is its speed. It's like the ultimate speedster of the universe, clocking in at an astounding 670 million miles per hour. That's fast enough to whip around the Earth more than 7 times in a single second. But here's the kicker, this speed is not just fast, it's constant. Whether you're standing still, flying in a jet, or hurtling through space at 1,000,000 miles an hour, light will always race past you at this exact speed. This universal constancy is a cornerstone of Albert Einstein's theory of relativity. Light speed also sets a cosmic speed limit, a barrier that nothing in the universe can cross. It's a boundary that governs the very nature of space and time. So, when we talk about the speed of light, we're not just talking about how quickly photons move. The speed of light is not just a number, it's a fundamental constant of the universe. Light isn't just white, it's a rainbow. This is because light is a spectrum of colors, each with a different wavelength. When all these colors come together, they create what seems to be white light. The spectrum of light visible to the human eye ranges from red with the longest wavelength to violet with the shortest. This spectrum, known as the visible spectrum, is only a small fraction of the entire light spectrum. Beyond the red end of the visible spectrum lies infrared, and beyond violet we find ultraviolet. But our eyes are not equipped to perceive these wavelengths. So how do we see colors? When light hits an object, some of it is absorbed and some is reflected. The colors we see are the wavelengths that are reflected back to our eyes, so in essence, the colors we perceive are the ones that objects do not absorb. The colors of light are as diverse as the universe itself. Light is more than just illumination, it's a tool. Let's delve into how we have harnessed this incredible phenomenon for our benefit. In technology, light is the backbone of modern communications. Fiber optic cables carry pulses of light across continents, enabling instant global connectivity. It's also a key player in data storage, with Blu-ray discs storing information in the form of light patterns. In medicine, light is a lifesaver. Lasers perform delicate surgeries with precision, while ultraviolet light sterilizes equipment. Infrared light, on the other hand, gives us thermal imaging, helping to identify inflammation and other health issues. In the realm of science, light is a window to the cosmos. Telescopes capture light from distant stars and galaxies, providing us insights about the universe's composition and history. Light also plays crucial roles in energy production, agriculture, and environmental conservation. Solar panels convert sunlight into electricity, while photosynthesis in plants provides the oxygen we breathe. From lasers to fiber optics, light is shaping our future. So, what is light? We've encountered an array of astounding facts, from ancient theories of divine entity to a modern understanding of its dual wave particle nature. Our understanding has been a winding path of discovery. We've learned that light is an electromagnetic wave, capable of traversing the vast emptiness of space at an unimaginable speed, but we can't help but wonder, what will future discoveries tell us about the nature of light?